All right, so I appreciate everybody's patience. I appreciate everybody coming back and getting ready to finish up this third section. We've been talking about matter and how to classify matter. We've finished up learning how to do problem solving, talking about metric prefixes, unit conversions, and dimensional analysis. We're moving into this basic idea about how to classify matter. We talked a little bit before about atoms, elements, molecules, and compounds. And now what we want to do is we want to take a little broader look at how matter is found in our everyday experience. We mentioned it briefly the last time that we got together. We did talk about matter being the way that we normally interact with substances, and normal I put in parentheses because normal is subjective. For introductory chemistry, we want to say that matter is the stuff that we interact with in our everyday lives from a normal perspective. But that doesn't mean there aren't other types of matter. I'll give you just one example. The plasma is a type of matter. The sun is a plasma. There are TVs made that take advantage of the properties of plasmas. But at the end of the day, it's not something that you can interact with from a perspective of, you can open the TV and you can put your finger in the plasma and stir it around. No, you can't do that. You can't go to the sun and take a cup full of plasma and deal with that. There are other matter. There's subatomic particles. That's matter. I mean, in all of its sense. In the fourth section, we'll talk about subatomic particles, but they're not matter in the normal sense. And so in this particular section, we are restricting our conversation about matter to be in the normal sense, the sense of how we interact with it. And so I did briefly mention that we can find mass in solids, liquids, and gases. Now, last time we were here, we talked about using this as a particle to represent an atom. And we talked about using this as a picture to represent a molecule. And I'll just remind everybody, remember they can be different colors because at the end of the day, there's different types of atoms. And so I just want to make sure that everybody's okay with that, and to realize that that's what we're going back to. We're going back to that particular picture of what matter looks like. We're using this as a conceptual model. And so using this as a conceptual model, these little dots, what I want to do is I want to talk about solids, liquids, and gases in those terms. I really want you guys to have a conceptual picture of what these things are at this level of the atom or the molecule. And so what I do is I want to draw circles. I want to draw little pictures of solids, liquids, and gases. And I want to use the model that we developed with the little dots. When I draw these pictures, it should have essentially all the information that you need to understand the definitions of what a solid, liquid, and a gas is from the particulate level. And again, what I mean by particulate level is the level of these dots, understanding things from that atomic picture. Okay, and so let's get on with solids. Let's do this. Let me change my colors. So what I'm doing right now is I'm drawing a simple atomic level picture of a solid. What you should be doing is you should be saying, well, what are some of the properties of this atomic level picture that he's drawing? What's going on with these particles? let's list some of the things that are happening here. One student says they're rigid, and that's absolutely correct. I've drawn a container that's round, and yet the particles are not taking, look there, there's some space underneath there. They're not taking the shape of the container. Also, look here, they're not flowing down the side of the container. They're rigid. They are, the particles are, for better term, stuck in one location. And they're stuck next to each other. Yeah. Another thing that you should notice that they're very close together. Eventually, you don't really need the words. You just need the picture. You need to notice that in the picture, we've got some particles. They're very close together, and they don't take the shape of the container, which means that they're rigid and they're stuck in one location. There are some other properties of solids that come out of this. The fact that these particles are stuck in one location and they're very close together. They're not easily, the shape of a solid is not usually easily changed. They usually can't be compressed very much. The volume can't change, which means, that's just another way to say they can't be compressed. So at the end of the day, the important picture is here. This is a solid. Small particles, very close together, stuck in one location. They can't move around each other. This little black particle can't become free and move over here. They're stuck in location. There's a little bit of a difference when it comes to liquids. Now, essentially, the particles are just as close together. I'm really at this level, I'm not going to draw them any further apart. But what is happening? What does it seem like it's able to do now? At this point, you should start to see that the particles that make up a liquid are able to conform to the shape of the container. But so what does that mean? That means that exactly. One student said, if it's able to take the shape of the container, then that means that the individual particles themselves can move past each other and change position. So this black particle can start there, but it can end up over here. This is what, so in other words, particles can move past each other. So the thing that is similar to a liquid and a solid is that the particles are still pretty close together. That works on both levels of the solid and the liquid. But once we've moved from a solid to a liquid, now the particles can move past each other, and that means they're going to be able to take the shape of the container. They're still not very compressible. Even though the shape is indefinite, they're still not compressible. And the reason that they're not compressible is because the particles are pretty close together. So it doesn't matter if I rotate this container, the volume of particles essentially stays the same. Now there's a difference, real big difference when it comes to gases. So there's that. And then there's one more thing that I need to do to change the picture to make it accurate. And I do it like this. I go, pew, 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 pew. What do these little tails mean? in your picture, you should indicate with tails or something like this that they're moving about. And I really did a poor job of making it random. And I'm going to go back and I want to do it a little better. I want to make it random. There we go. That's a little better. Now I'm doing a little better. Making it random. So does it take the shape of the container? But fills it. They're very far apart. They're in constant random motion. Okay. Yeah. Because gas particles are not really near each other and they're in constant random motion, they are free to move about the entire container. Okay. So what this means is that if I were to input a little green particle of gas right there, then eventually when I looked, it could be there, or maybe it would be over here, or maybe it would be over here, or maybe it would be over there, but it would be allowed to be anywhere in the container. Let's compact all the particles. The volume of the container is 1, 2, 3, 4, 5, 6, 7. The volume of the container is the volume of the entire circle. 1, 2, 3, 4, 5, 6, 7. There's all 7 particles of gas that I've now pushed together and made them really close together. This is artificial, but what I'm trying to illustrate is the volume of the particles compared to the container. The volume of the particles is very, very small compared to the volume of the container. If I were to arbitrarily put a lid on this container, then I can make the volume of the particles the same as the volume of the container. The same thing with solids. If I put my piece of solid in a little box that it perfectly fits in, then the volume of the container is the same, essentially the same as the volume of the particles. This will never be true with a gas. No matter, at some point, if you continue to add particles, it stops becoming a gas and it becomes a liquid. And that's a phase transition. And we're not going to really talk about phase transitions in this course. All right, so here are your pictures of solids, liquids, and gases. Does anybody have any questions about this? I want to just take a quick beat to make sure that I'm addressing any questions that come up with this particular thing. So let's go ahead and do that now. Type in chat if you have any questions. All right, so let's take a break. I mean, not a break, but let's take in what is going on with my, there we go. Let's look specifically at gases. And you don't, if I didn't tell you, you wouldn't know, but now we're going into the parts of chapter 11 that are specifically related to gases. And so I just want to bring them into the conversation now because it's appropriate to do so at this point. So I want to go just a little bit deeper into gases. What is one of the properties of a container that has gas? There's something that we typically talk about when we think about a container that's filled with gas. Well, a soda can, so the statement was soda can. A soda can definitely has both liquid and gases, but what happens when you squeeze the soda can? Can you squeeze it? what the gas in there has developed pressure. And what I want to do is talk about fire extinguisher as an example of a closed system that has some gas in it. There is pressure. Balloon. Balloon is a closed system. A gas cylinder is a closed system with gas. And all of these things about gases, all of these containers have a pressure. And what I want to do now is talk about the pressure of a gas as it relates to the definitions of the particles that make up a gas. When we look at the picture, we said here we got some particles. They're very far apart, but they're in constant random motion. So let's just take a look at one of these particles. Let's look at this particle right here. I'm going to use the purple. It's heading this way. So eventually, what's it going to do? It's going to collide with the container walls. This collision with the container walls is what develops pressure. The pressure of a gas is what is resulting from there being from a single particle hitting the walls of the container. So specifically, it's the force per area of the surface of the container. This is a simple definition. And the force is due to the collision of the gas particles on the wall of the container. But at the end of the day, a very specific definition that you can take even over to the physics class is the pressure is the force per unit area. So if I have this gas particle collide with the wall of the container, there is a force that little piece of area exhibits on the side of the container. How do you think the pressure changes if there's more particles flying around in the container? So if I add more particles, do you think that the force per area goes up or it goes down? Yeah, some people are starting to, exactly. So pressure it's direct. So it's in a closed system, it's directly related to the total number of gas particles. All right. Now, what I want to do is I want to just wrap it up, especially this piece in chapter 11, by invoking a particular set of rules for gases. It's called the kinetic molecular theory of gases. And the reason that I bring this up right now is that let me just go back to pressure real quick. I've seen some people say down. If one single particle develops a force by colliding with the wall and the particles never touch each other, then the thing is if I just continue to add more particles, then there's more instantaneous moments of force. So that means that the pressure goes up. So the pressure goes up and not down. Now, I'm bringing up kinetic molecular theory of gases because this is a more formal definition of what a gas is. And the reason I'm bringing it up now is that from the third section chapter 3 in the book that we're using now. It does talk about matter, and then it develops these definitions of solids, liquids, and gases. But then later on in way later on in the book, it brings up this particular model of gases. But this particular model of gases is almost identical to the definition that I've already shown you. What I want to do is I want to write down the specific things, and I want you to tell me or you don't have to tell me, but I want you to think about whether or not you already knew that based on the definition. So 1, a gas is a collection of particles in constant random straight line motion. Type in chat. Did we already know that? Yes or no? Y or N? We didn't know that? In my picture here, I didn't show these particles already in motion, and I'm even specifically talked about how it goes in this line directly towards yeah, it did. Absolutely. Yep. And so that's one thing we already knew. How about this one? There is a lot of space between gas particles. Did we know that one already? Yeah, we already knew that one. And we talked about the particles themselves have a very, very tiny volume compared to the volume of the container. This is another way to say that. There's a lot of space between the particles. One of the consequences of this is that it's compressible. All right, here's 2 things that maybe we didn't know. Gas particles do not repel or attract each other. We didn't know that. In the picture that I showed you from gases, it's not easy to include in the picture the information that the particles don't attract or repel each other. So this is a part of this is one part of the kinetic molecular theory of gases that you can't include in a picture because it's not easy to show that they're not repelling or attracting each other. Let me spell it right. Attract. All right. All right. So there's one other piece. And you don't know this one either. So. The average kinetic energy of the gas particles is proportional to the temperature. So this one's kind of hard to show in a picture, especially when it's just one picture. I might be able to put 2 pictures down there and change the size of the sweeping tails that are indicating that they're in motion. We can say this one's at high temperature, this one's at low temperature, but I don't think that's necessary at this point. I think that what we need to do is we need to take all of this in together in what I have on the screen right now. If you remember that off to the right, or left, hidden off the screen now, was a conversation about solids and liquids. And we talked about how their particles are arranged. And we're thinking about the definitions that way. We also use that same type of definition for gases. They're same made out of particles, they're far apart, but we additionally in the picture, we showed that they're in constant random motion, and we tried to indicate that that motion is in a straight line. What we didn't do in the picture was show that the gas part, so that took care of this one. And it took care of this part of the kinetic molecular theory of gases. The blue stars, these two guys, these were not shown in the picture, and there's something that you're going to just kind of have to put in your brain. Additionally, these particles are not attracting or repelling each other. They're pretending like each other doesn't exist. One way to personify them is to say they don't see each other. Another thing about the kinetic, can the gas particles randomly collide with each other? In reality, absolutely. What we say, though, is that there is no loss of energy between those two particles. That's in the ideal sense. But I'm pretty sure that Diana wants me to continue along this thought just one little bit. In real gases, there is actually some repelling and attracting forces that are going on. In this particular version, the kinetic molecular theory of gases, we're establishing some postulates on how we can describe gases, and ultimately we're going to use those postulates to develop an equation that describes a gas that fits this ideal model. It's called the ideal gas law. In this class, we don't even use the ideal gas law, so I'm not going to spend too much time thinking about it, but the formula for the ideal gas law is PV equals nRT. Pressure, volume, N is the number of particles, and T is the temperature. R is a constant, so it's called the gas constant. But I don't want to spend too much time on it. We're never going to use this formula, so you don't have to memorize it. But some of these things are true, right? We already know this. The pressure is directly related to the number of particles. We said that right up here. The temperature is related to the pressure, and that's sort of said right here. And that brings me to this next point. The other thing we didn't show in the picture is that the average kinetic energy, the energy of motion, is directly proportional to the temperature. In other words, the higher the temperature, the greater the amount of motion, and with all other things being equal, the greater the pressure would be, because the greater the force they're using to collide with the walls of the container. But they're all interrelated in this way. And so what you have to know is the following. You have to know everything that I didn't cross out. And for you, the good thing is there are really just definitions. Most of this is all a repeat, right? If you can draw the picture and examine the picture, then you can get all of the words that I circled and read this time. The definition for pressure might be something that you have to commit to memory, and these two extra postulates, which aren't shown in the picture, you might have to commit to memory as well. Is there any other questions? Because I want to move on from gases at this point. So I just let some folks into the meeting. I just want to remind you that if you get lost, come back. If you send me a text, I'll try to respond to it when I get a moment to look at it to make sure that I see that folks are stuck. I don't always get a correct notification that people are waiting in the waiting room. It depends on whether or not I have the participants list scrolled all the way up or not. I'll try to do my best to keep it that way. Again, does anybody have any question about gases or how we look at solids, liquids, and gases from a particulate level? Okay, awesome. So let's go back to this idea of matter. We're back into the third section. We finished. Maddie, remember R is part of that formula. You don't need to have anything in that formula. R is the gas constant. That's all I'm going to say about it. You don't need to know anything about it. All right. So what I want to do is I want to go back to our picture of matter and a broader classification of matter from the standpoint of some definitions. And here's the definitions that I'm trying to get to. When it comes to matter, I might broadly classify two different ways to find it. One in a pure substance, or two in a mixture. And so when I want to give you an example, I want to draw a picture of what I mean by what is a pure substance. Here's a picture of a pure substance. One version might be this. So I'm going to draw some walls just so I can separate it. Another version might be this. Here's some pictures of some pure substances. Here's another picture of a pure substance, and this one really does confuse students quite a bit. This one's a little bit tougher. Why is this one a pure substance? This one is a pure substance because, first of all, use A for atom or M for molecule? Is this an atom or a molecule? Yeah, this is a molecule. It's two types of elements. And not only is it a molecule, it's also a compound, right? It's also a compound. The fact is it has two different types of atoms, but they're bound together. So when I have two different types of atoms bound together, I consider that to be one single substance. It's like water, right? If you have pure water, even though water is composed of hydrogen and oxygen atoms, that collection of water molecules is considered a pure substance as long as there's nothing other than water molecules in there. So to finish off this example, I could have a pure substance of molecules like this. So there's a picture of some pure substances. Let's do mixtures. Here's a mixture. Let's use red. Right? The red and the black atoms are not bound together, so they're different types and they're different substances. Here's another picture of a mixture. I've got the red molecules and the blue molecules mixed together. And so I'm going to just pause real quick and see if there's any questions about mixtures and pure substances, because we're going to move on from there. Okay. When it comes to pure substances, I've already drawn the picture of the two different ways that we can find the pure substance. They can be elements or they can be compounds. And right now we have all of the language we need to draw pictures of what elements could be. Elements could be a collection of blue atoms. It could be, another option would be that it could be a collection of red molecules. These are elements because they only have one type of atom. It doesn't matter if they're atoms by themselves or connected with bonds to make molecules. Remember, as long as there's one type, then they are elements. Compounds. Remember, a compound has to be a molecule. So it has to be bound together. And not only does it have to be bound together, but it has to be different atoms. So here's a picture of some compounds, or of a particular compound. Okay. Any questions about those pictures? This is somewhat review from last time. I just want to make sure. Pause real quick, 1B. Any questions about the pictures that describe elements or compounds? All right, now getting into mixtures, now we got a little bit of a challenge. Mixtures, these are going to be brand new words. They can be homogeneous, or they can be heterogeneous. Homogeneous, I spelled that wrong, not momo. Homogeneous. Homogeneous means the same composition throughout the mixture. Okay. Yeah, thank you, Diane. Yeah, homogeneous, the same composition throughout the mixture. Heterogeneous means different composition throughout the mixture. And I'll just highlight, right? Different is what hetero means. Homo is what same means. Same and homo are the same, or what are the definitions. So heterogeneous, different composition, homogeneous, the same composition. And so let's draw some pictures though. Let's make sure that we have a picture. Here's one picture. Oops. This one is, let me back up because I've started to draw the wrong picture in the wrong location. So let's go to homogeneous because that's where I was trying to be. Get restarted here. And so I want to make sure that I show that it's the same composition throughout. It can also be a mixture of molecules, as long as the composition is the same throughout the entire mixture. It could be a solid, it could be a liquid, it could be a gas. These are examples of homogeneous mixtures. And so let's break it down to everyday life, right? If I were to think about, before we do that, let me get the pictures of heterogeneous. So here's a picture of heterogeneous, right? It could be there's an example of a solid heterogeneous mixture. It could be completely separated. There's some mixing going on over here, but the distribution of particles is not the same throughout the composition of the mixture. It could be completely separated though. We could have here might be a very simple depiction of oil and water mixture. This container has two different substances in it, the red substance and the blue substance, and they have not mixed in any way. There is an interface between them. This would be like oil and water. So now that we brought that up, let's think about some everyday examples. A heterogeneous mixture is where the composition is different. A homogeneous mixture is where the composition is constant and the same. And so let's think about some examples. I'm going to write this down. Let's write down sand. Let's write down soda, closed though. Closed. Let's do soda, open. Let's think of something else. Let's go ahead. We'll do oil. We'll do, Italian salad dressing. All right, let's do these things. These are all mixtures. Are they hetero or homo? What about sand? What about sand? Type in chat. So let's draw a picture of some beach sand. Got some sand particles. Maybe there's some chunks of black stuff over here. Maybe that's some tar. Maybe I've got some other red things kind of there. Maybe I've got a little piece of a seashell right here. Another little piece of a seashell right there. Some of this stuff over here. If you think about sand, yeah, there's a lot of little quartz crystals. But at the end of the day, the composition of sand is not consistent. And so what I want to do is I just want to stop sharing there and show you a picture from the internet just so we can make sure that we're on the same page. Oh, iPad, can you just please show me? Ah, here we go. Well, I'm really embarrassing myself right now because I intuitively don't know how to, like, I'm trying to tell Siri and trying to tell iPad, I don't want two windows open. I only want one window open. You don't seem to like care about that. So I keep trying to like tell it to go away. See, it just won't go away. Anybody want to tell me how to do that? It was really frustrating because it's supposed to be the most user-friendly thing in the world, and I just want it to go away, and there isn't a quick way to do that. Like, how do I get it to go away? I know I'm going off on a little tangent right now, but can I drag it over here? No, I don't want it over there. I want it to just go away. No, go away. It doesn't go away. It doesn't ever go away. So what I have to do is completely close Safari down, and then it'll open up on its own again. I swear I can close it, right? Swipe up and swipe up again. How many times do I have to swipe up? Press done at the bottom. I think I tried that too. I should have used my Windows computer to do this. Yeah, see, it's just, Google will just say, all right. Google will just say, hey, do you want to look at this picture? Apple thinks that I'm going to open the website. All right, so this is the best I can do, right? I can sort of show you this picture. This is the best I can do at the moment. This is from good old Home Depot. Here's a close-up picture of the sand. Does this look like it's the same composition throughout, or does it look like it has a different composition? Yeah, this is definitely a different composition. This is a heterogeneous mixture. Right now, what I want everybody to make sure they're doing is responding to questions in the chat window. So I apologize that we're hitting a block, we're going slow. You might be able to, if you decided to move the individual particles with a tiny little micrometer tweezer and rearrange them so that they're perfectly spaced out, you still won't have a homogeneous mixture, because look at the particle shapes. The shapes of the particles are different themselves. So you can never make it homogeneous. So sand is definitely heterogeneous. And so there's a couple of people that are texting me while we're doing this. I'm not going to immediately respond to them. If you want an immediate response to a question, please type it in chat. We'll use text messaging when it's the only option available to us. But up until this point, what I want to do is I want to use the chat window. So sand is definitely a heterogeneous mixture. What about soda when it's a closed container? It's got water, it's got food coloring, it's got flavoring, and it's got sugar in it. What do you think about that? Yeah, it's absolutely a homogeneous mixture. But what happens to the soda when you crack the bottle open? What do you see when you crack open the soda bottle? What makes it hetero? What form? It fizzes, exactly. There's bubbles that form. And the bubbles are definitely a different composition than the soda itself. So once you open that soda water, it becomes a heterogeneous mixture. What about Italian salad dressing? You got a little bit of vinegar, you got a little bit of olive oil, you got a little bit of garlic, you got a little parsley. Right, and in order to get it on your salad, you have to shake it up real good and pour it out there real quick, because as soon as you set it on the table again, everything starts to separate. So Italian salad dressing is an example of a heterogeneous mixture. Okay, I think we're doing okay right now for time. And so what I want to do is I want to talk a little bit about, we talked about how to classify matter, but now what I want to do is talk about how we think about how matter changes. So it involves this. It involves chemical and physical properties and changes. So the textbook definitely lists these two things separately, but they're closely related. So let's make sure that we got this on the right page here. A chemical property can only be noticed when the substance changes its chemical composition. Really what we're saying is that it changes its identity. If I have water, liquid, and I change it into water, gas, is that, in the chat window, yes or no, is that an example of a chemical change based on the changes in a chemical composition? So would I say that changing water from liquid to gas is an example of its chemical properties? I'm getting lots of different answers. I'm getting some no's and I'm getting some yeses. So did it change its identity? Its identity is its formula. What is this? What does this symbol mean? This is its state. This is its state. This is its identity. The formula is its identity. So is this an example of a chemical property, the ability of water to change from liquid to gas? It just changed its state. It just changed its state. So this is not an example of a chemical change. This is an example of a physical change. And so again, a physical change or a physical property is the opposite, is manifested without changing the chemical composition, without changing its identity. Okay. So if I take water liquid and I turn it into water gas, exactly, Nor, that's a good example, and we'll go through some examples here in a second. This is an example of a physical change. But if I take water liquid and I break it up into hydrogen gas plus oxygen gas, then that's a chemical change. And so how do I identify some chemical changes? There's some things that we can use to identify chemical changes from taking place. One thing is a color change. We can say, here's an idea, color change. Color change. That'll give you some idea that you get a chemical change. What else can we do? Let's see. Heat is produced or consumed. Heat is produced or consumed. So let's think about this real quick. If I take a lighter, your tongue is not, your tongue in a taste is not an appropriate tool to investigate chemicals. So Maddie, I'm just going to say, I'm not going to answer that question because you shouldn't be tasting chemicals. So whether or not a taste changes is irrelevant to this conversation. But if I take a metal and I put it into some acid and it dissolves, in this case, it really is a chemical change, and you're not sophisticated enough to see that. But let's think about this. What happens if I have a nice iron nail and it starts to rust? Is that a chemical change or a physical change? I have an iron nail and then I end up with a nail that's now rusty. What happens if I leave that nail outside and I let it continue to rust? It just ends up being a pile of rust, right? This is an example of a chemical change. What if I take that iron nail and I put it into a blast furnace and I turn it into molten iron? And it's red because it's hot. What if I melt it? Yeah, that's just a physical change. Okay, so here let's do this will be the grand finale on physical and chemical changes. let's take a lighter. Let's take a lighter. And a lighter is, I mean, a butane lighter, one that has gas, a liquid in it, right? Okay. It's got some liquid in it. What happens when I depress? Physical change is just solid, liquid, or gas, right? State of change of state. That is. So let me rearrange your statement so that it's the most accurate. The change of state from a solid liquid to a gas, or vice versa, or in any way in between them, is an example of a physical change. I don't want to say physical change is just change of state, because I could take a piece of metal and I could hammer it out from a cube to a sheet. I didn't change its state. It's still a solid, but it's definitely a physical change. What's an example of another physical change? I can have something that's cold and I can just make it hot, right? I didn't change its state, but I just changed its temperature. That's a physical change. So what happens if all I do is press the lever? What if I do, if I press the lever and I let out the liquid and it turns into a gas? Is that P for physical or C for chemical? Right. Now, that's just a physical change. Now, this time I'm actually going to strike the wheel and set it on fire. Physical or chemical? Yeah, I'm starting to see lots of C's. Exactly. This is the idea of a chemical change. All right. And so what I want to do now is I want to do one last couple of things just to make sure that I'm wrapping up this bit of chapter. So it shouldn't take too long. All right. One thing that we need to know is that even in a chemical reaction, in any change, this is chemical or physical, the total amount of mass is constant. So that means that in general, I describe all changes this way. I have some reactants and they change to products. And it doesn't matter if I'm talking about a physical change or I'm talking about a chemical change. This is what's true. The total mass of reactants equals the total mass of products. And in fact, in order to make it actually true, I need to do this. But I'm not going to introduce that just yet. I'll save that for chapter 6. So at the end of the day, if I put 100 grams here, then I'll get 100 grams of water gas. If I put 100 grams of water and I get 60 grams, let's do this, and I get 70 grams of O2, how many grams of hydrogen are there? The total mass has to be the same on both sides. So whatever the mass of hydrogen is, it has, when I add it to 70, it must equal 100. So the mass of the hydrogen must be 30 grams. Yeah. Okay. All right. This is a good question. Is this implying that mass cannot be destroyed or created? If we think about it from an introductory chemistry standpoint, that's generally true. When we think about it from a more universally physical standpoint, it's not true. What we bring into in that case is this formula for Einstein that says what really is constant is energy in the universe, but it's the total sum of both energy and mass that is constant, right? Because what Einstein ultimately told us is that energy is mass and mass is energy. So there's a total conservation of energy. And while the amount of mass might be able to change, the sum total of energy in the universe is constant. And so, but from a general introductory chemistry perspective, in a chemical reaction, the mass does stay constant. And so there's two different levels to think about that. I hope that answers your question. All right. And so the last thing that I want to bring up then is energy. We measure energy in the unit of joules. J. And 1 joule equals 1 kilogram times meters squared over second squared. This is its relationship, and you can think about it from the kinetic energy formula, 1/2 mv squared. Well, the mass should be given as a kilogram. The velocity should be meters per second. So if I take, and I'm just examining the units now, kilogram, and I multiply it by meters over second squared, I get kilogram times meters squared over second squared. And so because this is kind of clunky and bulky and a lot of stuff to write, we said, okay, let's just call that a joule. So the energy unit that we're going to use is going to be a joule. And I mentioned to you earlier that, but first of all, there are different types of energy units. Another type of energy unit is the calorie. And 1 calorie equals 4.184 joules. Where else have you heard calories from? Where else have you heard calories from? Yeah, food items. But a food item is actually a kilocalorie. That is 1 food calorie. And so we call it kcal. And there's also another one that's commonly heard of in homes. Spell it right. The kilowatt hour. The kilowatt hour. These are some units of energy. Yeah, food, that's definitely nutritional. Okay. And so there's one last little thing that I want to throw out there, and that's this. Energy of the energy of a substance is related to its temperature. And so what I'm going to say is that the energy is proportional to the temperature. And there's two ways that we measure temperature in science. Now, the way that we measure it in normal, everyday experiences is that we measure it in Fahrenheit. In the Fahrenheit scale, water freezes at 32 degrees and it boils at 212 degrees Fahrenheit. And the relationship between Celsius and Fahrenheit is that you can get the Celsius temperature by taking the Fahrenheit temperature, subtracting 32, and from the result, dividing it by 1.8. We can also have the Celsius scale. This is very common. It's based on water, where water freezes at 0 degrees and it boils at 100 degrees. But the problem with both of these temperature scales is they both have negative temperatures. And for mathematical purposes that I'm just going to say it's because of math, negative temperatures cause a problem. So we came up with the absolute scale, the Kelvin scale, K. This is degrees Celsius plus 273 degrees. So for water, water freezes on the Kelvin scale at 273 Kelvin and it boils at 373 Kelvin. But the big deal is that the lowest possible temperature is 0 Kelvin. So that means there's no negative temperatures. So I know that at the end of the day, that was sort of just throwing some stuff at you about energy. But what should you be able to do? And we can do in some practice. We won't do the practice for this part today, but we will do it another day. What should you be able to do? You should be able to convert between units of energy. And I'll give you the per expressions or the equalities. For example, I'll say 1 little c calorie equals 4.184 joules. I'll give you something like that. There is no temperature colder than 0 Kelvin. So what if it's colder? It can't be. It's impossible. That's what we're getting at. Okay, you should be able to convert between energies of units, and remember all are units of energy, and I will give you equalities. So in other words, you should just be able to write a per expression. 1 calorie is 4.184 joules, or you should be able to write 4.184 joules is 1 calorie, and use those in a conversion problem. But you should also be able to convert between temperatures. That means Fahrenheit to Celsius, Celsius to Fahrenheit, Celsius to Kelvin, and Kelvin to Celsius. If I wanted you to go from Fahrenheit to Kelvin, you would have to go to Celsius first. There is no, there's no direct formula. I mean, you could derive one, but we're not going to. In my class and in my class alone, I typically will give you this formula, but I will not give you this formula. So you need to memorize that Kelvin is Celsius plus 273. Okay, what I'm going to do is I'm going to stop right there.